Good morning, everyone. My name is Kasidis Teerasuchai. I'm currently a student from Simpangkot University, Thailand, with suggestion from my advisor, Assistant Professor Butylene Sapabut, Associate Professor Manop Panapoy, and Assistant Professor Natu Chayut. It's an honor for me today to deliver this presentation. The topic of our project is preparation and property of the polybutylene succinate porous scaffolds by fused deposition modeling and salt leaching technique. Okay. In this presentation, I will cover 5 sections: introduction, objective, methodology, result and discussion, and conclusion. And now let's move to the first session. In the first sessions, I will going to talk about scaffolds. Scaffolds are a 3-dimensional structure here to deliver cultured cells or drugs to repair and restore the infected tissues. This particular design leads scaffold have suitable for use as a drug delivery device, such as being porous and can be designed in various shapes. And I will talking about the drug delivery device. Drug delivery device is a drug carrier into the body and directly to the target area. The efficiency and safety of using drug can be raised by controlling the release rate to adjusting the total amount of drugs required for the therapeutic effects. Okay. Because of drug delivery device usually has to be implanted into the body, especially in the case of preventing infection of the surgical wounds inside the body. Therefore, the material to be fabricated must be completely non-toxic to the body at all, while the drug is released, and of course when it decay. Polybutylene succinate is an outstanding choice with properties that can be decomposed in the body that does not cause any toxic substance during the decomposition and are well compatible within the body. And FDM technique, or fused deposition modeling technique, is one of the most widely used additive manufacturing processes for fabricating the prototype and functional parts in various plastics. Is it also a powerful tool to create patient-specific porous scaffolds by modifying the input materials to adjust local drug delivery capability? This is the extraordinary techniques we choose to fabricate our scaffolds with precise shape combined with salt leaching techniques, the simple method to produce pore in the material. This allows us to control the absorption and release rate by controlling the pore size and adjusting the porosity of the material. Objective of this project are to fabricate the porous scaffold by FDM and salt leaching technique, to study the effects of sodium chloride concentration on the morphology, porosity, and wettability of the scaffolds, and to study the effect of type of radar patterns on the morphology, porosity, and wettability of the scaffolds. For the method, we start with sodium chloride. Sodium chloride was ground and sieved to obtain the particle size in the range of 38 to 75 micrometers. And we create the polybutylene succinate sheet containing 4 different sodium chloride amounts were prepared by solvent casting method. This cast sheet with specific weight ratio of sodium chloride was cut into the small pieces and then molten and mixed in a co-rotating thermal screw extruder to form an extruded filament. This filament with certain amounts of sodium chloride was installed in 3D printing machines to construct the scaffolds by SEM techniques. Scaffolds were fabricated with two radar patterns, triangle and grid. The salt leaching technique was conducted to dissolve sodium chloride and to obtain the sodium chloride stainless porous scaffolds or NGP scaffolds. We also call this NGP scaffold. And this scaffold without filling with sodium chloride at all has been called sodium chloride free porous scaffold or NFP scaffolds. In the leaching process, construct scaffold embedding different sodium chloride content were immersed in the ionized water. This process continued until sodium chloride was completely dissolved. This was checked by dropping a few drops of silver nitrate solution into the ionized water, and no trace of white silver chloride precipitate was detected at all. And in table 1, we list the code name of the scaffold studied in this research with different amount of sodium chloride and different radar patterns. Okay. For the characterization, we use the characterization technique for investigate some properties that could affect the control release rate. The first one is morphological observation by scanning electron microscope or SEM technique. The second one is porosity measurement by density determination kit. And the third one is contact angle analysis by USB digital microscope. For the result and discussion, I will start with discussion about morphology observation of NFP scaffolds and MGP scaffolds having different salt content and data patterns shown in figure 1. This image reveals that the shape of the fiber of NFP scaffold shown in figure 1 column 1 was less stable to maintain fiber shape than NGP scaffolds, which could be due to the viscosity effects. The NFP scaffold exhibit a relatively smooth fiber surface more than NGP scaffolds. When the amount of salts increase from 40% by weight to 60% by weight, the surface of the NGP scaffolds become rougher. The number of pores increases and pore size was larger. However, there was no effects of the radar patterns on the fiber surface morphology of the scaffolds containing different salt content. Okay, in this in figure 2, this figure 2 shows SEM images of chiropractors and NFP scaffolds and NGP scaffolds having different amounts of salts and data patterns. The morphology of NFP scaffold shown in figure 2 column 1 and NGP scaffold shown in figure 2 column 2 to 4 display the same fashion as those on the fiber surface, with sodium chloride dispersion quite well. The measured pore size was shown in table 2, indicate that with the salt content increase, the more salt particles agglomerate within the filament, forming a larger pore size. However, according to the SEM images, it was clear that the pore size and the number of pores on the fracture cross-sectional surface were larger and more generous than those on the fiber surface. This implies that salt particles tend to occur in the matrix rather than on the surface. Although the scaffold contains different amount of salts, and the radar pattern did not affect the fracture cross-sectional morphology of the scaffolds. Okay. This is the result of the porosity of the scaffold. The porosity is represent the void space within it. The porosity of our scaffold calculated by this specific gravity determination method was shown in figure 3 and summarized in table 3. The NFP scaffold with grid and triangle radar patterns exhibit 38.12% and 40.05% of porosity respectively, which show that the triangle occupy a bit higher white space than the grid. All the NGP scaffolds display greater porosity than the NFP scaffolds due to the dissolution of sodium chloride during the salt leaching process. It was found that the porosity was directly related to the salt content. The higher of the salt content, the greater of the porosity. Moreover, the porosity of the triangle was higher than the grid, and the difference between two patterns was more pronounced when the salt content increased. It could be because theoretically, as we fix in 80% in fields of FDM techniques, the triangle radar patterns consume more filament to fabricate the scaffold than the grid. For this reason, the triangle occupy a greater porosity. The contact angle testing result of NFP scaffolds and NGP scaffold with different radar patterns were shown in figure 4 and tabulated in table 3. The NFP scaffold showed no difference in contact angle between two radar patterns. But on the other hand, the NGP scaffold were higher in contact angle value than NFP scaffolds because the rough surface caused by a small pore left by the salt result in increase the hydrophobicity.
Sorry, we have 3 minutes remaining.
Okay, thank you. And when focusing on two radar patterns of NGP scaffolds, the triangle radar pattern has a lower contact angle value than the grid patterns. It's was found that the triangle pattern has more space or more void between filament in the scaffold structure, which increased the influence of gravity force on the water droplet. The gravity force that was promoting the adhesive force that competing with cohesive force. Thus, the competition between this force was more inclined toward to adhesive force, result in decrease of hydrophobicity for the triangle patterns. The surface property of wettability helps us determine the use of scaffold to apply a drug release control. Since the purpose of this study was to use the scaffold as a drug carrier into the body that has a medium water lightness, imply that scaffold with more hydrophilic might be easier to reach for the medium. For this reason, the scaffold we made in a triangle radar pattern should probably be a better option. For conclusion, therefore, conclusion in this research. The first one is PBS NGP scaffold were successfully synthesized by FDM and salt leaching techniques. Second, the leaching process also successfully create a large number of pores in the NGP scaffold with various shape size, depending not only on the amount of salts, but also on the radar pattern too. The third one is the porosity of NGP scaffold increased with the increasing proportion of salts. The contact angle measurement indicate that NFP scaffold show no difference in contact angle between two radar patterns. And finally, NGP scaffold with grid patterns exhibit more hydrophobic than the triangle patterns. Okay, thank you for your attention.
Okay, thank you very much for your nice presentation. And this time is the for question and comment. Is there any question from the audience?
There was no question from the audience now.
Okay, so for me, as you said, so now you fabricate the sample, right? One is the grid pattern, and
Yeah.
the next one is the triangle pattern.
Yes.
I wanna know why is the different. I mean, can you move to the the hydrophobicity and hydrophilicity? Why is the different? Yeah. This
Right, yeah.
slide.
Yeah.
You can see from the contact angle, right?
Yeah.
I mean, why? So for my first question, why when you increase the porosity, right, the contact angle is not so different?
Oh, okay. Because some property that influence or affect the contact angle in terms of porosity. I think the amount of porosity on the surface of the fiber is
Yes.
is more affect to contact angle than the porosity in the inner fiber. But when we increasing the salt content and is referred to increasing the porosity, right?
Yes.
The increasing of this of all of the porosity is almost in the inner fiber, not in the surface.
Yeah.
Yeah.
Also, so that's why, right? The reason.
Yeah.
And also so for my just now for my previous question, the different you said in the conclusion, right? The grid pattern of the sample is more hydrophobic than the triangle pattern, right?
Yes.
Can you explain the reason?
Oh, okay. I will explain this with when I will start with compare about the NFP scaffold to NGP scaffold at first.
Yeah.
The NGP scaffold with have many porosity that will cause the fibrous surface more luster, right? And this more rough of the surface will cause the contact angle value higher. And it mean is more hydrophobicity. Okay, but when we focus about two radar patterns about grid and triangle. In triangle patterns, we found that when we create this when we create our scaffold with two data pattern, grid and triangle, we fix the percent of infills in when we use FEM technique. So when it created when it fabricated our scaffolds, we found that in triangle pattern, it has more void space between filament between filament line that create the triangle shape compared to the filament line that create in square shape of grid patterns. So
yes.
So we think that in triangle pattern when when the void space is more bigger, then I think the gravity force that affect to the water droplet is more influence to the water droplet, and this make contact angle value lower and or more hydrophilic.
Oh yes, I see. That's all of your reason. And okay, so I just have the one question. Why? So now your effect, you vary the amount. Sorry, it is the time.
Yeah, it's right. We run.
Oh.
Okay. If so now the time is limit. It's okay. So now we will move to the next speaker. And thank you very much for your presentation.